Hi, welcome everyone to this video. What we are going to do today is give a little proof of how can we show that given a random variable x with an exponential distribution with parameter lambda, the earth moment is equal to this formula. Mu prime sub r equals to r prime divided by lambda to the power r. So let's start. If you remember the first case of the moment, we know that mu sub r prime equals the expected value of x. This x, remember, is the random variable distribution. Which in our case was exponential. Okay, so having this first thing into account, let's continue. There are basically two ways to make this calculation for the expected value. So the first one is like this: the expected value of a continual distribution integral from minus infinity to plus infinity x, every point that we are testing in the distribution, and the product with the image of that point in the function. This is the general definition, the intuitive definition of the expected value of a continuous distribution, but this is not the one we're going to use. We are going to use a special case or property, and it's the following. So the expected value of a random variable composite by a function g is defined as the integral from minus infinity to positive infinity, the function that we are composing, and the product by the original function distribution. Okay, so we are going to use this second formula that we have here, this one. Okay, let's continue. Now what we are going to do, we are going to just apply that formula. If you remember, we have a random variable x, and we want to investigate the behavior of the earth moment. So what we are going to use the second formula in the following way. So the expected value of distribution x to the power of earth, this is like g of x. Well, this is a composite function of given a power, so that's because we can use the second formula. So expected value of distribution x to the power of r is equal to integral from minus infinity to positive infinity x r, remember, the composite function, versus product by the original function, which was exponential lambda e to the power minus lambda x. So this is our first step, and from now on things will be much easier having this into account. What we are going to do next, this is a small trick, we can call it. We want to dispose this part, but if you remember the exponential distribution, the probability negative exponential, it's something like this. So for negative values, if you make the integral of this region, it's 0. So we can convert this initial part of the integral to 0. So let's continue. The expected value of x distribution to the power of r is equal to integral from 0 to plus infinity xr, which was the composite function, product by lambda e minus lambda x, because this is an integral, don't forget the dx. Okay, so in this step we just convert this first part of the integral to 0, but that's an acceptable step, because what we explained in the function, all images of probability negative values have an integral of 0, so don't worry. The reason because of what we just made that is because we are going to make a transformation to make things easier, and this is the heart of this proof. So right now let's remember the function gamma. Function gamma has this formula. It's pretty well known in statistics. Function gamma is the function gamma with a variable t. It's the integral from 0 to plus infinity x to the power t minus 1 multiplied by e minus x. So remember, this is the lambda function, like a weight r, it's the notation, and that function has some very interesting properties that we are going to use. So what we are going to do right now, we are going to convert this expression into something like this, the gamma function. If we achieve that, we are going to use a very special property from the gamma function, and we are going to end the proof. But we need to continue right now converting this into this. Okay, so let's go. So let's copy again the formula, just because I want you to see it all. So the expected value of a random variable x to the power of r equals integral from 0 to infinity x to the power of r product lambda e minus lambda x dx. Okay, so let's begin. Let's begin the transformation that I told you about. So transformation is pretty easy. Let's just do the following. If you remember integral calculus, this will be pretty easy. But if you don't worry, we are going to go step by step. So let's create a new variable u, and let's say that u is lambda x. So if we made that transformation, then we must do the following. we must obtain a new value for the dx. So du is the same that lambda dx and the reason for that is that we just differentiated on both sides. So the derivative of u and the derivative of lambda dx. X is a variable, lambda is constant, so we obtain the derivative of u and lambda dx. So let's continue. The first thing, we are replacing the variable of this expression with an u. We won't use x but u. So we differentiate on both sides of our equation. U equals lambda x. We differentiate, so we get du equals lambda dx, differentiating by u and by x. And the second thing we do here is this. So we get the new value of x. So x equals u divided by lambda. This comes from here. So that's this is an easy step, don't worry. Now we've gotten these two expressions, but the most important thing is we need to replace the dx, this dx. So we already, with this formula, we can do that. So dx equals du divided by lambda. Or also, if you prefer, we can see this as 1 divided by lambda by du, exactly the same. So what we are going to use right now are these two identities, these two formulas, and we are going to use them on this. So let's see what we get right now. So let's go. The expected value of a function distribution x to the power of r is equal to our expected value of our new variable u, and this we define as the integral from 0 to plus infinity we are just replacing, remember, this x we are changing using this second formula. So we u divided by lambda to the power of r multiplied by lambda by e minus u, and this is multiplied by our new dx, by dx is 1 divided lambda du. So we can cancel this lambda out and this fraction out, and we get this. Expected value of u is equal to Remember, we are going to get here u to the power of r and lambda to the power of r. So because this is a constant, we can take out. So we get this 1 divided lambda to the power of r. This is out because it's a constant. Integral from 0 to infinity u to the power of r. It's this part of the expression multiplied by e minus u du. So this formula will be very helpful because this is in fact the formula of gamma function. So if you don't remember the gamma function, we showed it up at the beginning, but we're going to show a version right now so it's clear. So this is the special case that we'll be using right now. Gamma function of variable t plus 1 is equal to integral from 0. Remember, we use right now 0 because this distribution doesn't have to consider negative values, to infinity x to the power of t e to the power of minus x dx. So remember, this is just the gamma function that we are using right now. And this is actually the same form that we are working here up. So integral from 0 to infinity, integral from 0 to infinity, variable to a power, variable to a power, and variable to power, and an exponential to power. Here r is rt, and u will be the x. So we just have an expression with the same form of a gamma function. Oh, I'll say it again. I believe I did make a mistake. Parameter t is r and x is u. T in the canonical form of the gamma function is r, and the x in the classic form to express gamma function is u. So, having made this transformation, we are going to use this beautiful property of gamma function that, given the gamma function of a value t, which value is +1, this is the same as having the integral okay, I just made a mistake. Okay, now The property that we're going to use is the gamma function of a variable t plus 1 is the same as 1 divided lambda to the power of r. Okay, I apologize, guys. I just made one more mistake. This wasn't the property, it's just that I am using my notes. So the property is our gamma function of t plus 1 is the same as n factorial. And that's all we need. Gamma function of value t plus 1 is n factorial. So, going back to an original expression, the expected value of variable x to the power of r is the same. Remember, we just took out this constant, 1 lambda r, and because we showed that this is a gamma, that the expected value of u, that is an appropriate conversion of our variable x, is same as a gamma function, we can use the gamma function property. T plus 1 is n factorial. So we are going to replace that integral with this, r plus 1. Remember gamma function. And because of this expression, we will just replace this, and we can get, finally, okay, so finally, applying the factorial property, we can infer our result. We've just proved that mu sub r prime, dr refers to the case, dr name as you want, the earth moment of a distribution function is equal to expected value of variable x to the power of r, which we showed is equal to r factorial because of this a property of gamma function divided by lambda to the power of r. So we finished. So that was all, dear viewers. I apologize because I knew I confused a bit. This is my first video. I just didn't find any explanation on this formula, and I believe it could be helpful. So if it was helpful for you, please give a like. It will make me happy. I'll try to improve my next videos. So have a nice day. If you have any questions, you may leave them in the comments. I didn't explain the gamma function. That's in many statistics books, but if you want, I can try to make the proof. Just leave me a comment. So have a nice day. Goodbye.